Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous, Mumbai, I welcome you all to the today's session. Our today's guest is Dr. Dipak Jadhav, sir. He is an associate professor at Department of Mathematics, Srimati CHM College, Ulhasnagar. He will deal with the topic of sequence and series today. Over to you, sir.
Thank you. Okay, so we have already discussed few problems on infinite series in last lecture. Today we will continue discussing further more questions on infinite series. So here is a question. I hope it is visible to all of you.
Yes, sir.
Okay. Let's start with an easy question. Think on this. There are two series given. S1 is summation n from 1 to infinity n square plus n plus 1 upon n into n plus 1, and S2 is some other series. You want to conclude whether either of them converge or both of them diverge or both of them converge. The first one is n square plus n plus 1 upon n into n plus 1. So what do you feel? Is it convergent or divergent?
Sir, can we use the ratio test?
Ratio test. You try using the ratio test.
Okay, sir.
Divergent, sir. S1 is divergent.
Yeah. How do you conclude it is divergent? Yeah.
By comparing with series summation 1 by n square.
Okay, good. So summation 1 by n square with this. With this, you have compared this, but this is convergent.
No, sir.
Yeah. What is an here? N square plus n plus 1 upon
N into n plus 1.
n into n plus 1. So that's nothing but n square plus n plus 1 upon n square plus n. Where does it goes as n tends to infinity?
So 1.
1.
Yeah. So what I can say by necessary criteria is divergent. Yeah.
Yes, sir.
Good. Because if your series is convergent, then an goes to 0. What about n2? S2. Square plus 1 upon n square plus 1. Here, if you choose Bn as this, square upon n cube plus n square, so it goes to 0. Bn goes to 0. So you cannot apply necessary criteria. So choose. The trick is choose Cn as what is the highest power of n in the numerator? 2. So choose numerator term n square, and what is the highest power of n in the denominator? 3.
N cube.
So choose n square upon n cube. That's nothing but 1 by n. Choose CNS 1 by n for all n. And try computing limit n tends to infinity of mod n upon Cn. n square plus 1 upon n square into n plus 1 into, you are dividing by Cn, so it will get multiplying, yeah,
It will tends to 1.
yeah, it will tends to 1. So,
1. Sir,
which is
what is the what is
yeah,
the necessary criteria?
necessary criteria is this. If summation an is convergent, then an should go to 0. This is the necessary criteria.
Okay, sir.
So contrapositive of this will imply if an does not tends to 0, then summation an is divergent.
Okay, sir. Fine.
So here what we can conclude, which test we have applied here, limit form of, no, limit form of comparison test, summation bn and summation cn behaves alike. Limit form of comparison test. Yeah, I hope all of you remember.
Yes,
But
sir.
what do we know about summation cn?
Divergent.
Divergent.
Yes, very good. It's divergent as being a harmonic series. So summation bn also diverges. So both will diverge. So which option is correct?
Option D.
Yeah, very good. Here is another question. Is it visible to all of you?
Yes, sir.
So what the question says, an is equal to n plus 1 for n in n. Then we want the sum of the series. So we not just have to conclude whether it is convergent or divergent, we also want to find its sum. So what do we want? Summation n from 1 to infinity minus 1 raised to n plus 1, an plus 1 upon n factorial. This is what we wanted to actually compute. So that means the series is convergent series. The series is convergent and we want to find its sum. So how will you?
But sir, if n tends to infinity, then n will also tend to infinity. So 1 by n will become 0. But that first n will also tend to infinity, no?
Yeah. So where does an goes as n tends to infinity?
To infinity.
Yeah. Yes, absolutely fine. No worries. But here we do not just have an. Here we have an plus 1 upon n factorial. So denominator is going towards infinity faster than numerator.
Okay, sir. Got it.
So the necessary criteria will be satisfied. So n from 1 to, let me write. At least you can try substituting what is an plus 1. If an is this, then what is an plus 1?
N plus 1 plus 1 by n plus 1.
Yeah, good. Upon n factorial. Now, is it possible to do something? Now I can split the denominator. So let's split the denominator, n upon n factorial plus 1 upon n factorial plus 1 upon n plus 1 into n factorial. Is it okay?
Yes, sir.
Yeah, good. Now what you will get? Summation 1 to infinity minus 1 raised to n plus 1. The first term is 1 by n minus 1 factorial. Second term is 1 by n factorial. And the third term is 1 upon n plus 1 factorial. Now you multiply minus 1 raised to n plus 1 inside and separate the sum. N plus 1 by n minus 1 factorial plus is it allowed? Means can we do
Yes, sir, we
this?
can do it.
Yeah, good. Because we know the series converges. We know the series converges. Okay.
Yes, sir.
Now we just have to compute the sum. So what is the first expansion? If you expand it, 1. The first term is 1 in the first expansion. Let us expand the first term. Let's expand the first term only. First term is 1. Second term is minus 1 upon
1
1
factorial,
factorial plus 1 upon
2
factorial
factorial,
minus. Yeah. So there are alternate plus minus. Plus. Second expansion is
1
1 upon 1 factorial minus 1 upon 2 factorial plus 1 upon 3 factorial minus 1 upon 4 factorial. And the last is
1 by 2 factorial.
yeah. So is it reminding you the sum? Is it reminding you about any function?
Yes, sir. E of x.
Okay, so what do we know about e of x? E raised to x is summation x raised to n upon n factorial. That is 1 plus x upon 1 factorial plus square upon 2 factorial plus x upon 3 factorial. So how will I get the first one,
So replace
second one, and
x by minus x. Then we replace x by 1.
x? Yeah. So simply you replace x by minus 1. No?
Yes, sir.
So x equal to minus 1 will give you 1 minus 1 upon 1 factorial plus 1 upon 2 factorial minus 1 upon 3 factorial and so on. So the first one is e raised to minus 1. How much is second one?
Sorry, e raised to minus 1 minus plus, I think.
1 minus e raised to minus 1.
Yes.
And what about the third one?
So 2 minus.
Third one is e raised to minus 1. Because this addition is 0, I hope. 1 minus 1, that's 0.
Yes, sir.
So the final addition will be then e raised to minus 1 plus 1 minus e raised to minus 1 plus e raised to minus 1. So we'll have 1 minus e raised to minus 1. Please check out the
1
computation.
plus e
So
inverse.
1 plus, sir.
1 plus,
E inverse.
okay, 1 plus e inverse. Good. So option is D. Is that okay? Did you follow all of this?
Yes, sir.
Good. So let's move on to next question. Yeah, this question. Let us see this. So this variety of questions are also appeared in past papers, where the sequence an is not directly given. It is only said something about the sequence an, and then we want to see whether series summation an, summation an by n, or n times an, series summation n times an, whether it is convergent and divergent, and so on.
Sir, is option C is correct?
Okay, let us check whether C is correct or not. What about others? What is given? An converges to A and A is strictly greater than 0. So I can readily conclude about series An. Yeah. So which result I am applying here?
Necessary. By necessary criteria.
Series An is divergent. Good. Now if An goes to 0, then An by n, sorry, An goes to A, so An by n will goes to 0. I think this much is fine. If An goes to A, then An by n will go to 0 as n tends to infinity. Yes, very good. But necessary criteria does not tells that if Bn goes to 0, then summation Bn is convergent series. We cannot say anything like that. Yeah.
So summation n diverges and summation 1 by n is again divergent.
Okay. So can you say two series diverges, then summation an into bn converges? Can I, or divergent? Can I say like this? Do we have anything
No,
related
sir.
to? No. So algebra of convergent series only tells you about if two series are convergent, then their addition is convergent. But it does not tells you about the two series are divergent, then what will happen to their addition, their subtraction, and their multiplication, and so on. So how many of you feel that this series is convergent? How many of you feel this? And how many of you feel this is divergent? Because anyway, this option to ruled out. And this option, because the first option says summation an converges. That's not true. We have already seen. So possible option is option C is also ruled out, I hope.
Yes, sir.
This option C also says summation an converges. So this also ruled out. So we have either one of the two option, either B or D. One of them is true. So
Sir, maybe an by n should converge.
Okay, so do you believe it depends on an, that an by an
Yes.
may converge in some cases, and some cases it may divergent? This is what you want to say?
Yes, sir, approximately.
Okay, so you feel that in some case it may converge, some case it may diverge. What about others?
So by necessary condition, it will converge.
What is which necessary condition you have applied?
Sir, an by an tends to 0, then their
Yeah.
summation will always convergent.
No, that's not true actually. See, summation 1 by n is divergent. We all know this. But what is 1 by, where does 1 by n goes? It goes to 0. So even after 1 by n going towards 0, your series is divergent. The series is divergent. So necessary criteria, the converse of that is not true. Necessary criteria holds only in one direction. So here I have written only in one direction. See, if summation n is convergent, then n goes to 0. I haven't written any converse of this because the converse is not true actually. And this is the counter example. This is the counter example. 1 by n goes to 0, but still the series is divergent. So you cannot conclude by using necessary criteria that series an by n is convergent. See, if I choose, see, suppose if I choose, suppose an is 1 for all n in n, then where does an goes?
Goes to
An
1.
goes, yeah, as n tends to infinity. In this case, what can you say about series summation an by n? What this will become?
Divergent, sir.
Divergent.
Diverges.
Yeah, so divergent. So I have at least one counter example wherein the an satisfies the hypothesis of the problem and the series an by n is divergent. Series an by n is divergent. Can I have one counter example in which case it is convergent? Is it possible?
Sir, an could be n.
Okay, but in that case, hypothesis is not satisfied. In that case, the sequence an will not converge to some finite number, it will shoot to infinity.
Yes, sir, right.
Yeah. Okay. So it seems that it's not easy to find any counterexample for the sequence an going towards some constant fixed positive number and the series an by n is convergent. So we'll try in another way proving actually it diverges for any value of for any sequence n satisfying this hypothesis. So what I want to say, this is not correct. All the time an by n is also diverges. Whenever you have sequence n converging to a, this series also diverges. Is it possible to prove? Am I audible to all of you?
Yes, sir.
Okay, so
Sir,
some of
it should be possible to prove, but we are not getting any way to prove.
okay. So let me just write one line. Then say what is given. An is a sequence converging to a. So can you write definition? What does that mean by definition?
Limit n tends to infinity or n equals a.
Yeah, good enough. Good enough. So what does this says? Limit n tends to infinity, an is equal to a, and a is greater than 0. So I can apply the definition by epsilon n naught definition. What I can say?
Given epsilon greater than 0,
Yeah.
there
There
exists a natural number
There exists a natural number n such that
mod of an minus a is less than epsilon
for all n
for
greater
all
than equal
n
to,
greater than equal to.
yeah, good. So you expand this inequality, what I will get? Minus epsilon less than an minus a less than epsilon for all n greater than equal to n. Yeah. Then you add a minus epsilon less than an and a plus epsilon for all n greater than equal to n. Is it okay? Yeah.
Yes, sir.
Up to here it is fine. Good. Now, is it possible to choose some epsilon? Because this is true for any epsilon. So is it possible to choose epsilon and conclude about the series divergence of the series? So a is positive. So suppose if I choose epsilon as epsilon, I can choose anything. Suppose epsilon is equal to a by 2. So what I'm going to get? A by 2 less than an less than 3a by 2. Yeah.
Yes, sir.
Yes. And now you generate a sequence which we are talking about an by n. Now you divide by n throughout. What you're going to get? A by 2n less than an by n less than 3a by 2n. Now from this, is it possible
The
to
squeeze
conclude the
theorem.
series divergence? No, no, no. We are not applying
Sir,
any
can we
Swiss
apply
theorem.
squeeze theorem?
What we will get after applying Swiss theorem?
Sir, maybe we can conclude that an by n will converge.
Yeah, yeah. So that too we already know, na? An by n goes to 0. Thus we
Yes.
already observed. We are talking about series summation an by n. So can I say this series is dominated by this series? Sorry, this series dominates this series.
Yes, sir.
And what do we know about summation a by 2n? What can we say about this series? A by 2 is anyway constant, so I can put out 1 by n is divergent. Can I say?
Yes, divergent.
Yes, sir.
So what can I say about this series now?
So overall, it will be divergence.
Yeah. So since it is a series on upper side, it will diverge. So by which test?
Comparison test.
Yes, very good. So this was it a difficult argument?
No, sir.
Or is it easy?
It was actually difficult to choose the correct epsilon, sir.
Yeah. But anyway, I want an epsilon so that a minus epsilon is positive.
Right, sir. Got it.
Yeah, good. So I hope it is followed to all of you. So option D is correct. Option D is correct. Both will diverge. Now try out this. we want to find those values of alpha for which it is actually convergent. So what is the series here? Summation n from 1 to infinity, 1 plus alpha by n whole raised to n square. So what is an here? 1 plus alpha by n whole raised to n square. So this series is convergent. This series is convergent. But we want to find those particular alpha for which it is convergent. So there is a power. Whenever there is a power, it is always tempting to use root test. So by root test, what we can say? Mod an raised to 1 by. So that is nothing but
1 plus alpha by n to the power n.
yeah, raised to n. What is the limit of this as n tends to infinity?
E to the power alpha.
Yeah. As all of you got this limit as e to the power alpha.
Yes, sir.
So what do we know about root test? If it is less than 1, the series convergent.
Right, sir.
To the power alpha less than 1, then series is converging. Okay. Okay. So e to the power alpha less than 1 means alpha is less than 0. Yeah. Can I say like this?
Yes, sir.
Yes, sir.
So it's convergent for alpha less than 0. I hope it's followed to all of you.
Yes, sir.
Yes, understood.
Yeah, good. One easy question. This. I hope you understand the difference between necessary and sufficient.
Yes, sir. Sir, is it B?
B. You mean B or D?
B, sir. B for Bombay.
Okay, so you feel both of them are sufficient.
Aha, sir. Means if any of the condition is proved, then maybe we can conclude.
So if this is true, does that imply series converges?
No, sir.
No. So
The first condition is necessary, not sufficient.
yes, very good. This is only a necessary condition, not sufficient. Necessary
Okay,
means
got
what?
it, sir.
Yeah, necessary means what? If your series converges, then you must have this n goes to 0. ये होना ही चाहिए आपके पास. ठीक है.
Right.
And yeah, and the second condition by root test,
The
if this
option
condition is
C.
yeah, by root test, I can say if the second condition is true, series converges.
Series
So second
converges.
condition is sufficient. Yeah. So option C. First is necessary. It's not sufficient. It is only necessary condition, and the second is actually sufficient condition. Because if second condition happens, your series is convergent. Yeah. Is it okay?
Got it, sir.
Sir, it's happened.
Yes,
That means
very good.
vice versa. Yeah, anything.
Yeah,
That
can
means,
you please repeat the question?
sir, in second, the limit n tends to infinity, n to the power 1 by n is equal to 0. Then from back side, we can say
Yeah,
that the series is convergent.
series is convergent. Yeah. So that says this is a sufficient condition.
Okay, sir.
This is a sufficient condition because if this is true, your series is convergent. Your series is convergent by using root test. Because in that case, the value of L is less than 1. So I can apply root test and I can say the series is convergent. Yeah.
Yes, sir.
Is it okay?
Yes, sir.
Okay, okay. Now the one more easy question. But look at the option. Absolutely convergent, conditionally convergent, divergent, none of this. So I hope you know
Absolute
term
convergence, sir.
and conditionally convergent. I hope.
Yeah.
Yeah. So the series is actually absolutely convergent.
Because it is the e to the power minus 1.
Yeah.
Sorry.
Yes. Yes. But how does it matters whether it is e to the power minus 1? When I say absolute convergent, what I need to see then?
All positive values of the if I
Mod of
sum of the
So for absolute convergent, I have to actually check this series.
yes,
And
yes.
this is E. Yeah.
Uh,
This E. Is this E?
E minus 1, I think.
E minus 1. Yes. Very good. This is E minus 1. It's not actually E. One
Yes.
term is missing. Yeah. So for absolute convergence, you have to take the absolute values of the terms and then you have to take the series, whether it is convergent or divergent. If it is convergent, we say the original series converges absolutely. But what do you mean by conditional convergence?
Sir, if series
If
is
summation
convergent,
an is convergent, but summation mod an is divergent,
Not convergent.
then we say your series is conditionally convergent. Then summation an is conditionally convergent. I hope this is known to all of you.
Yes, sir.
Okay. One more question. Yeah, it is. Is the question visible?
Sir, my end it is not visible to me. Just previous two questions are visible. Yes, yes. Just till now visible. The investigate of the convergence is the
Okay,
question.
okay.
Okay.
Yes, yes, yes.
Okay. Okay.
Investigate the convergence of this. Is it convergent or divergent? And so on.
So divergent.
it is convergent, sir.
But I also think it should diverge because n raised to 4 should increase rapidly, more rapidly than e raised to minus n square.
Hello, sir.
Yes, yes.
Sir, here an will be n to the power 4 by e raised to the power n square. So, in the denominator, that is e raised to the power n square will rapidly tends to infinity. So, it will the an will be converged to 0. So, the series will be divergent.
Which criteria you have applied?
Sir, necessary criteria.
Just a minute.
Sir, hello. Am I audible, sir?
Yeah. Yes.
Yes, sir. Am I audible?
Yeah, you are audible.
Yes, sir. I am using the limit comparison test. That is, I am choosing n to the power 4, e to the power minus n square. It is a n whole, and bn I am taking as 1 by n to the power 4.
Bn you are taking 1 by n to the power 4. Yeah. So
Yeah.
yes, you can take that. So what is limit intensity of mod an by bn?
It is still 0.
Yeah. So there's e raised to minus n raised to 4 e to the power minus n square.
Yes, sir.
You are dividing by bn, so we'll go like this. Yeah. Where
Yes,
does it
sir.
goes? Where does it
It
goes?
is 0.
N raised to 8 upon e to the power n square. It
Yes.
goes to
If
0.
I Yes, yes. And that is why in the previous class you have told that this is one side true. I think if Bn is 1 by n to the power 4 is convergent always. That is why it must have to be convergent.
Yeah, yes, absolutely correct. I hope this is fine for all of you. This limit goes to 0.
Yes, sir.
This limit goes to 0 because this infinity by infinity form. So you can go on applying L L'Hopital rule repeatedly, and you can conclude this limit is approaching towards 0 by repeated application of L'Hopital rule. So
Sir, sir, here you apply a limit comparison test, limit form test.
yeah.
So, but in limit form test, we have to get a finite and non-zero. But here we get a 0.
Okay. Then what
Then
you will do?
how? So can you apply this form if we get a 0?
Yes, you can apply. What does the form of comparison test says? See, this limit is 0. If this limit is 0, what does that mean? This implies for every epsilon greater than 0, there exists a natural number n such that mod of mod an by bn minus 0 less than epsilon for all n greater than equal to n. This is the definition of convergence of a limit. Yeah.
Yes, sir.
This implies mod of an upon mod of bn is less than epsilon. This implies mod of n less than epsilon times mod bn. So choose epsilon as 1 because it is true for any epsilon. So in particular, it's also true for epsilon equal to 1. Yeah.
Yes.
So what you will get? Mod an less than mod bn. And there's a series on upper side. Yeah.
Okay, sir. Got it.
So by comparison test, I can actually say since summation bn is convergent, so summation an is also convergent. Yeah.
Yes, sir.
Comparison test, summation n is absolutely convergent. So convergent as n raised to 4 is convergent. Okay. But I want you to observe this by using this way. Look at here, all of you. What do we want to conclude? We want to conclude or we want to investigate the convergence or divergence of the series. So here an is what? N raised to 4 into e to the power minus n square. Yeah. That's nothing but n raised to 4 upon e to the power n square. Yeah. This is what. Now e raised to x. I know the power series expansion. What is that? 1 plus x 1 factorial plus x square by 2 factorial plus. Use this power series expansion. What you will get here? n raised to 4, 1 plus n square upon 1 factorial plus n raised to 4 upon 2 factorial plus n raised to 6 upon 3 factorial. Yeah. Plus n raised to 8 upon 4 factorial plus let's on continues. Is it okay?
Yes, yes.
Yes, sir.
Okay. Now I am deleting all but one term from the right hand side. I am keeping numerator as it is, and denominator I am just
N to the
keeping
power
n raised
4,
to
6.
n raised to 6 upon 3 factorial.
Yes.
I am
Obviously,
yeah. So I
it
am
is
deleting.
less than from.
Yeah.
Uh,
Do you
now,
believe it is?
yes.
Yeah.
Then easily get comparison.
Yes. Good. So this what is this? This is 6 upon n square. Yeah.
It is obviously convergent by p-test.
Yeah. Good. Is convergent by p-test. So by comparison test, summation an is also convergent.
But
So I want all of you to observe this. This way also you can tackle this problem.
yes, sir.
So I hope this solution is understood to all of you.
Yes, sir, clear.
Okay. Let's try one more. There are two sequences AN and BN, and we want to conclude about series AN and series BN. Whether any of this is convergent or whether any of this is divergent.
Sir, limit of Bn is
Yes, can you repeat again? Summation Bn is?
no, sir. Actually, I was thinking about the limit. Limit is actually tends to 0.
Yeah. So both of them goes to 0. Good. AN also goes to 0 and BN also goes to 0 because of this exponential factor. Okay. Because of this exponential factor, both of them goes to 0. So you cannot apply necessary criteria. You need to think of something else.
Sir, maximum value of sin n is 1, so we can
Yes.
say that e to the power minus 2n is less than equal to
Sin in
e to the power
1 e raised to 2h. This is less than equal to 1 upon e raised to 2a. Yeah. Good. So now,
By comparison test, the series is convergent.
but what about this? Why this is convergent? You're absolutely correct, but you need to.
Sir, by ratio test,
So do you means don't you recognize this with some standard series?
Sir, it is geometric series.
Yes, perfect. This is actually 1 upon e square raised to n. So you can compare it with this. Yeah. This. So what is R
yes,
here? 1 upon
1
e
by
square. Yeah, it is less than 1. So this converges by geometric series test.
yes.
By geometric series test is convergent. Thus, by comparison test, summation n is convergent. Thus, by comparison test, Summation an is convergent. What about Bn? What is Bn here? N square sin n whole square upon e raised to n. So this is less than equal to n square by e raised to n. Yeah.
Yes, sir.
And by the same logic that we have applied in the previous problem, I can actually write expansion of e raised to n. 1 plus n upon 1 factorial plus n square upon 2 factorial plus n cube upon 3 factorial plus. I just need to choose the correct power. So which power I will choose? The minimum possible power?
N to the
N
power
raised to
Three by
power
four.
4.
4.
N raised to 4 by 4 factorial. So that is equal to 4
4
factorial
factorial
by.
upon n squared.
So this is convergent by P series test. Yeah.
Yes, sir.
So by comparison test, summation Bn also converges.
Converges.
I hope it is followed to all of you. So both converges, option C.
Yeah, sir.
Yes, very good.
Yes, sir.
Yeah.
Sir, one thing we can see, suppose if we divide n by Vn, then from single test we can conclude the same, I think, because here then directly it is followed from the limit comparison form.
So An by Bn you want to say?
Yes, yes, sir.
What is An? E raised to minus n square e raised. Sin n upon e raised to 2n. E raised to minus. Yeah, you can also use that. Very good. Bn is e raised to minus n square sin n whole square. This goes to 0. Yeah.
Yeah.
Where does it goes? Yeah, it goes to 0. So by limit form of function test, you can say it is converges. Very good.
Okay, sir. This is the new question. U1 is equal to 1 and n is equal to 2 minus 1 by n. Okay.
Yeah. I hope it is visible to all of you.
Yeah.
So we do not want to find out whether the series is convergent or divergent. We actually want to find its sum. So whenever we want to find out sum, there are only few tests. Either you apply the definition or you try observing it is telescoping series, or you apply geometric series test. That's it. Only in these three cases you can actually calculate the sum. Or you may have some standard expansion of series. So let's try computing Sn here. What is Sn? So let me call this term as Bn. So Sn will be B1 plus B2 plus B3 plus Bn. So what is B1? 1 by A1 square minus 1 by A2 square plus what is B2?
1 upon a2 square minus 1 upon a3.
Yeah, yes. 1 by A2 square minus 1 by A3 square. B3 will be 1 by A3 square minus 1 by
A4
A4
is
square. The last term is 1 by An square minus 1 by An. So are there any terms getting cancelled? I hope. You know, observe.
1 upon
This,
a1 square minus
yeah, all the
1
terms in
upon
between terms. So we are left with 1 upon a1 square minus 1 upon an plus 1 square. So what is the limit of this as n tends to infinity? So Sn converges to 1 by a1 square. Where does an plus 1 by n plus 1 will go? Where does an goes?
So 2.
2.
2. So where does an plus 1 will go?
So
2.
2.
Yeah, that's a silly question. Okay, so 1 upon an plus 1. It will go to 1 by 2. Yeah,
So is it converts to -1?
minus 1. What you will get here? 1 minus half, no? It's half.
1 by 2.
Oh, sorry, sir.
3 by 2. No, sir. So we have to square now.
So what you will get? Okay. So 1 by n plus 1 will go to 1 by 4. Yeah. So this will go to 1 minus 1 by 4. So 3 by 4. Now is it okay?
Yes, sir.
Let us do this question. Is it visible?
Yes, sir.
This is from 2025, the last year's question paper. The sum of the infinite series. See, we do not want to again check whether it is convergent or divergent. It's already given it is convergent, and we want to find its sum. That's it. So let me expand it first of all. Pi raised to 2n plus 1 upon 2 raised to 2n plus 1 factorial. So for n equal to 1, what you will get? Pi upon 2 cube into 2 factorial minus n equal to 2.
So pi cube.
Pi cube upon 2 cube into 4 factorial, not
सर
6.
फर्स्ट टर्म में
4
पाई
factorial.
क्यूब होगा.
Pi cube.
Yeah. First term is pi cube. The second term, 7.
5, sir. 5, pi to the power 5.
5 to power 5.
Yeah. Pi to the power 7. And what is
5.
denominator?
5, sir.
5,
5.
sir.
5 to the power, sir.
Yeah. Pi raised to
2.
5, and the denominator is
5. 2 raised to
2 to the
power 5.
okay, 2 raised to power 5. The next term, pi raised to 7 upon 2 raised to 7 into 6. The series is actually convergent. This is already given convergent. But we want to find its sum. Where does it converge? So there are only few results. Either you can apply definition, or it may be a telescoping kind of series, as in the last example, or you may apply GST, or maybe standard expansions. So here you can observe it's not easy to compute sequence of partial sum, because it is not of the type geometric series. It is not of the type telescoping, and it's not easy to compute the sequence of partial sum. So you cannot apply any of this. So possibly you may have some standard expansion. So what are the expansions we know? We know few of them: e raised to x, sin x, cos x, or maybe log of 1 plus x, 1 upon 1 minus x, and you differentiate this, integrate this term by term integration. By integrating term by term or by differentiating term by term, you get few more expansions. Using this, you may try to calculate this infinite sum. So which expansion will help here? What is there in the denominator? See, 2n factorial. Did you see this 2n factorial?
Yes. Cos x.
Okay, so by observing this 2n factorial, what is trigger in your mind? Which standard expansion contains 2n factorial?
Cos.
Cos. Very good. So let's try using the expansion for cos x if possible. What is cos x? Yeah, anybody knows the expansion for cos x?
1 minus x square by 2 factorial plus x to the power 4 by 4 factorial, and it likes goes on.
Yeah, very good. All even powers. Yes. And this is true for all x in R. It has a radius of convergence infinity. Yeah.
Yes, sir.
Yeah. So now how will I generate this out of this? I got 2n factorial.
Sir, do we need to take common pi cube by 2 to the power cube into 2 factorial? And then 1 minus something created like the expansion of cos x?
Yeah. From this series only, you have to generate this expansion somehow.
So can we take common pi cube by 2 cube, pi cube divided by 2 cube into 2 factorial?
From this infinite sum, no?
Yes, sir.
Yes, you can take absolutely fine. So this also you can write it as pi by 2 you are taking common, I hope.
No, sir, pi cube. Not from the sum, the expanded side.
Hmm?
Or we can go in this way as well.
Now, can you correspond this and this? Because you need even powers, no, on this side.
Sir, if you take
Oh.
pi by 3 in the expansion series of
Sir, if we take pi by 2 common, then we can easily.
Yeah, so you put cos x as pi by 2. So what you're going to get? 1 minus pi by 2 square upon 2 factorial plus pi by 2 raised to 4 upon 4 factorial minus pi by 2 raised to 6 upon 6 factorial. This is what you will get. So that's 1 minus pi square upon 2 square into 2 factorial plus pi raised to 2 into 2 upon 2 raised to 2 into 2 into 4 factorial. Yeah. This is pi raised to 2 into 3 upon 2 raised to 2 into 3 into 6 factorial. Yeah. 1 minus pi square upon 2 square into 2 factorial plus pi raised to 2 upon 2 into 2 into 2 factorial minus pi raised to 2 into 3 upon 2 raised to 2 into 3 into 2 into 3 factorial. Did you get the required sum? Does this corresponds to this?
Yes,
Yes.
only taking a minus.
Yeah. So can you solve and tell me the final answer?
1 minus cos pi by
That is 1.
And you need pi by 2 here. So this will be equal to then pi by 2 times 1 minus cos pi by 2. You mean to say something like this? Is it okay for all of you?
Yes,
Yes,
sir.
sir.
Okay. Okay. Try out this problem. Or maybe can discuss this problem. So hint is compute sequence of partial sum. And then find its limit. You will get the answer. Okay. Compute
Okay, sir.
sequence of partial sum and then find its limit. Because there is a log, so that will help you. For
Okay.
example, yeah. So log of this plus log of this n terms. So by using property of log, it's log of this. Yeah. And then you can
Yes,
simplify,
sir.
you'll get the answer. Yeah, you'll get the answer. Try out this. This is different question. Consider the expansion of fx is equal to this. So fx is given 3 upon 1 minus x into 1 plus 2x. In powers of x, we want to expand this in powers of x. That is valid for mod x less than half. So they have given the domain for the expansion of this. So how will you expand this in powers of x? What method you will apply to expand this?
First I break into partial fraction, and then in the denominator it is easy to see that it is a infinite geometric progression type something.
Okay. So how will you break this in partial fraction?
Yes, I am breaking in
So
such a way.
okay, you are trying to break it in partial fraction.
Yeah.
What about others? Okay. So do we know the series expansion for this 1 upon 1 minus x? That's this,
Sir. Yes, sir.
and this is valid for mod x less than 1. Yeah.
Yes, sir.
Do we know the series expansion for this?
One plus 2x plus 2x the whole square.
1 minus 2x plus 2x the whole square. Alternate plus minus you will have minus 2x the whole cube plus 2x whole raised to 4 minus. And this is valid for mod 2x less than 1. Yeah. Mod x less than half. Is it okay up to here?
Yes, sir.
Yes, very good. So how much is this? Actually 1 minus 2x plus 4 x square minus 8x cube plus 16x raised to 4 minus and so on. Yeah. Now I want to compute power series expansion for this. That's nothing but I already have the power series expansion of the first. And I also have the power series expansion of the second. So is it possible to multiply? Yeah. Is it possible to multiply?
Sir, here
Yes, sir.
In fact, it
formal
will not.
multiplication method I think would not work here because both are containing infinite
Infinite.
element term.
Yes, correct. You cannot simply multiply 1 to this full bracket and then you multiply x to full bracket and then you multiply x square. That won't work. You'll means get lost. Like it's very difficult to understand what is a product in that way.
Sir, I have breaking into partial fraction as given term is 1 by 1 minus x plus 2 by 1 plus 2x. And that is why we can add those term by term. Okay.
1 upon 1 minus x.
1 by 1 minus x plus 2 by 1 plus 2x. I think between two plus, it is plus, not minus.
It is plus. So let's check this.
Yes.
Let's check this. So what you will get? 1 minus x into 1 plus 2x. Here you will have 1 plus 2x plus 2 minus 2x. Yeah, correct. You can do that way. And then it's easy to add.
And sir, in this case, we are not bothering about the multiplication of term by term because here term by term we can add those series. Okay.
Yes, absolutely. You can get the answer by using this partial fraction. But I
And some
want
of
you
the
to,
term will get cancelled.
yeah,
Some term may get cancelled and the expression will be like more efficient or
Okay, so absolutely fine. You can means in this addition, you can expand this and you can expand this, and you'll have addition, and you definitely compute the coefficient of x raised to 4. But is it not possible to multiply these two infinite series?
Yes, I think, sir, I am clear clearance about this concept. There are some product in called quasi product of two.
See, it's not very difficult to understand this product. You can understand this product term by term. For example, what will be the constant term in the product?
1.
Constant term will be constant term from here and constant term from here. Yeah, that's a
Yes.
constant term in the product. What is degree 1 term? You multiply x with 1 and minus x with 1. Yeah, sorry. I hope I'm audible to all of you.
Yes, sir.
Yes.
So we are trying to compute the degree 1. So how will you get degree 1 term? So 1 into minus 2x plus x into 1. That's only possible degree 1 term. Yeah. Other terms will obviously have, means it's a crisscross multiplication. See, 1
But
x.
sir, we have to calculate the expansion coefficient of x to the power 4 now.
Yeah. So I'm just explaining how will you actually compute the product term
Okay.
by term.
Okay.
Product is computed by term. So if I want x coefficient of x raised to 4, I need to I need to pick up first 5 terms from the first bracket and 5 terms from the next bracket. Then how will I get the x raised to 4? I multiply this with this. Yeah.
So yes, sir.
Then multiply this with this.
Mm.
Then multiply this with this. Then multiply this with this. Finally, multiply this with this. That will only give me term corresponding to x raised to 4. So what is that? What is the coefficient of x raised to 4 now? 1 into 16. Yeah. Minus 8 into 1. Plus 4 into 1. Minus 2 into 1. Plus 1 into 1. That's a coefficient of x raised to 4. Yeah. So how much it is? 16 minus 8 plus 4 minus 2 plus 1. That is
11.
how much?
11.
11, sir.
Okay. Sorry. So it is 11 x raised to 4. Okay. So this is what we have got in this expansion. But what is our term? 3 times this. Fx is 3 times this. So what is the coefficient of x raised to 4 then? 3 into 11, that is 33. Yeah. Is it followed to all of you? Absolutely, you can apply partial fraction. There is no harm in applying partial fraction. You just have to add this. So what you will get after adding this? 1 plus x square plus x plus 2 into 1 minus 2x plus 4x square minus 8x cubed plus 4x raised to 16x raised to 4. Yeah. So what is the coefficient? 33 from here. 1 plus 2 into 16. Yeah. So both ways you'll get the
Yes.
correct same answer. Yeah. No worries. So the idea behind explaining this problem is you can, though it's looks like both the brackets infinite sum, it's a series and it's a series. So you want to multiply these two series. So at a first glance, it seems impossible to multiply these two series. But actually, if you think term by term, then you can carry out the multiplication. You just have to think what is a constant term. Then you have to think what is a degree 1 term. Then you have to think what is a degree 2 term. Is that okay? Coefficient of x is to 0, coefficient of x is to 1, x square, coefficient of x cube. In that way, you can actually write down the multiplication of these two infinite series. I hope it is followed to all of you. Do you have any doubt in this?
No, sir.
No, sir.
Okay, so I wish best of luck for all of you to appear for this exam jam. I also like to thank organizers of the Wilson College for allowing me to lecture in this jam lecture series, jam workshop. Yeah. So we will stop for today. Yeah.
Participants, if you have any further doubts or queries, you may ask to sir one by one.
Sir,
Yes.
can you find the value of summation I equal to 1 to n, 1 by 2 raised to n plus 1 into 1 by 3 raised to n minus 1?
Can you repeat the problem? Summation?
I equal to 1 to n, 1 by 2 raised to n plus 1 into 1 by 3 raised to n minus 1.
I equal to 1 to n, 1 by
2 raised to n plus 1.
I
The whole
plus 1.
raised to 1 by 2, the whole raised to n plus 1.
N plus 1 or I plus 1. Running index is I here, na?
Yes, I plus 1.
And
1 by 3, the whole raised to I minus 1.
okay, so you want to compute the product. It's a finite sum, I hope. So if you expand, what you will get? 1 by 2 square and 1 by 3 raised to 0 plus 1 by 2 cube and 1 by 3 1 by 3 raised to 1 plus 1 by 2 raised to 4 into 1 by 3 square plus 1 by 2 raised to 5 1 by 3 cube. Is that what you want?
Yes,
1
sir.
by 2 raised to plus 1 by 3 raised to n minus 1.
Sir,
Yes.
sir, can we
Yes.
separate 2 raised to iota plus 1 as 2 raised to I into 2 and 3 raised to I minus 1 as 3 raised to I upon 3. So 3 by 2 is common and 1 upon 2 raised to I into 3 raised to I.
Yeah. So this is 1 upon 6 raised to I divided by 2 into
1 by 3.
1 by 3. Yeah.
Yes.
This is 3 by 2 and summation 1 by 6 raised to I. Yes. Now it becomes a geometric series, I hope.
Yes, sir.
Now you can compute this. Okay.
Is this limit equal to taking separate products and multiplying the limit?
What
Like
can you
summation I equal to 1 to n, 1 by 2 the whole raised to I plus 1 into summation I equal to 1 to n,
no
1 by 3
no
raised.
yeah no you
But
cannot
the product of two absolutely convergent series will converge to the
yeah summation an is convergent and summation bn is also convergent. In fact, here it is not series, here it is finite sum. Yeah. So if you have a1 plus up to an and you have another bracket b1 plus b2 plus up to bn, if you multiply this, will you going to get a1 b1 plus a2 b2 plus a3 b3? Is that what you will get after this? Are these two equal?
no, there will be more terms.
Yeah. So that's what you only answered your own question. Yeah. Is it okay? Did you follow this?
Oh, yes, sir.
Very good.
Sir, I have a question regarding to this power series only. You have discussed in the rigorous way, but if I can revise this text from which source you would refer for this exam purpose? Only power series portion. And
Okay, which textbook, which
yeah,
reference book you can refer?
yes, sir. That is why the logical confusion, whichever may be arise in I'm getting
Yeah.
to.
So there is one good book, Real Analysis by Somu Sundaram. This book has plenty of solved problems on almost all topic, means all topic belonging to real analysis. So you will get, and if you want only problem solved, then you can also check out this book, Tom series. Sham series on power series. Sham series. These books are available in each topic, in vector algebra, in linear algebra, in matrices, in calculus, one variable calculus, multivariable calculus, in real analysis. So you have to search a book which contains examples solved on power series. So this particular book has only solved problems. That's it. No theory.
Oh,
Only
oh,
definition, statement, and you'll get only solved problems in this. But I will prefer the Soma Sundaram book. This contains plenty of solved problems.
okay,
You can
okay.
also read calculus, Thomas and Finney, calculus, Thomas and Finney calculus. This book also contains solved problems on infinite series. Though the name is calculus, it also contains problems on infinite series. Yeah.
Okay, sir.
Is this
Yes.
okay? Yeah.
I hope there are no more queries left. Dr. Deepak Jadhav sir, we are deeply grateful for your presence. We appreciate the time you took to share your knowledge with us. Thank you for your valuable contribution to this lecture series through your four such a wonderful sessions. We are honored to have you with us, sir, and we look forward more such sessions with you, sir. And also I mean, thank you so much for your kind words, sir.
Yeah.
Thank you so much, sir.
Thank you. Thank you so much. All the
I
best.
now I now invite the participants to kindly express their words of gratitude towards our esteemed resource person. While doing so, please make sure your video is on. So, any volunteers? Participants, we have shared feedback form link to the chat box to the Deepak search session. So please check that. And I request you all to kindly give your valuable feedback. Please note that next session will be on 8th of September 2025 from 6 p.m. to 7 p.m. as per the schedule. So let us meet there. Goodbye.
Thank you, Dipak sir.
Yeah, yeah. Thank you.
Thank you, sir. You are great teacher, sir, and your knowledge have give more power to attempt in IT jam examination. Thank you, sir.
Thank you.